Hey everyone, welcome back to 3 Deviations. In today's video of multivariable calculus, we want to talk about properties of vectors. So we spent the last video talking about vectors as a concept, and now we're going to start talking about how we can use vectors, some of the mathematically rigorous properties that we know of vectors, so that we can be well-versed in these properties and simple operations, like we discussed the elementary addition, difference, and scalar multiplication properties. We'll just put all those together in this video and consolidate before we move on to vector products, which will be a little bit more complicated. Also, just to preface this video, I'm having a little bit of a cold right now, so forgive me if I sound a little bit out of it. Alright, anyways, I've just got all the properties here. So we're going to say that A, B, and C are vectors, and these are going to be in an n-dimensional vector space. So vector space is just where these vectors live. So, for example, of the vector space V3 is where all of our three-dimensional vectors live. So these are V3 has a vector V, or, well, I guess vector V is in V3 such that V is a three-component vector with components A, B, C. Likewise, we can have two-component vectors as well. That would make up the two-dimensional vector space. So anyways, we also have D and E, which will be scalars. So we have the rule that we determined from the parallelogram law last video, such that A plus B equals B plus A, right? So if I add one vector to the other one, it's the same if I do the reverse. Similarly, if I want to add three vectors to one another, I could do them in whatever order I like. Furthermore, if I add A to its negative, then I get the zero vector. So if I have vector A, which looks like this, and I have vector negative A, which looks like this, then that's equal to 0, so I get the zero vector. Furthermore, if I want to do a scalar multiplication on a sum, I can take all the vectors separately. So D times A plus B is equal to D times A plus D times B. All right, finally, we have two more. We've got if I just perform this operation, if I do D times or D plus E times A, I can distribute the A as well, so I get D times A plus E times A. And finally, if I want to multiply the C here times A, and if I multiply C times D times A, or maybe I do, these are both scalars here, so this should be an E, actually. So if I have E times D times A is equal to E times D times A, it doesn't matter the distributive properties how I do that. All right, so now I'd like to discuss our second topic, which is basis vectors. Now, basis vectors are very important. It basically postulates that we can build any vector from a set of basis vectors that form an orthogonal basis. So what do I mean by this? So if I have the xy coordinate plane, and I have any vector, so this could be any vector, I can build this out of series of jumps in the x direction and series of jumps in the y direction out of units. So basis vectors are really just adding vector quantities to our components. So we can define three-dimensional space with linear combinations of basis vectors. So I can define V as being equal to alpha times I hat, which is the basis vector in the x direction, beta times j hat, and then gamma times k hat. So that's basically what that's saying. So essentially what we get is I, j, and k forming a basis that can sweep out the whole plane. All right, that's what I've got for this video. In the next video, we'll talk about vector products. Thanks for watching. We'll see you next time. Bye.